We've talked a bit about mini batches, true stochastic gradient descent, and all these are looking at a continuum from how many of the elements from our training set are we looking at before we actually update the gradient. So what is the number of them that we're trying to get an average gradient on? And we can either do 1 or all the way to k, where k is the number of elements in the training set. So 1 is, let's call it true stochastic gradient descent. K we'll call batch gradient descent. And something in between we'll call mini batch. Now, it's a little confusing because sometimes people talk about batch when they mean mini batch. If we're talking about mini batch, we always mean something less than the total number. But if you hear the word batch, it's a little bit unclear as to whether they mean mini batch or they mean everything. So just kind of be aware as you're looking in the literature. If you are using batch gradient descent, the advantage is you have the true gradient that you want to be using. Whereas if you're using some fewer number, you're just getting an estimate of the gradient. And in the case of just looking at one element, you're getting maybe a not very good estimate, an estimate with high variance. So you might think, well, if we could, we'd always like to do it this way. Okay, but if we look at our epochs, right, we're going from 1 to the number of epochs. If we're using this batch gradient descent, then every epoch, we're updating the gradient once. Okay? So in this case, per epoch, if we've got 1 mini batch and batch, how many updates to theta? In batch, we have 1 update. In SGT, GD, we have k updates. And in mini batch, we have k divided by the batch size. So the most updates here, the fewer updates here. Why does that matter? Well, the reason that matters is a lot of the cost of computing the gradient is actually just computing the gradient for every one of the training instances, right? So here in this case, we're computing the gradient for all k training instances and then updating theta once. Here, we are also, when we get to the end of the epoch, we have looked at, in batches, in mini batches, the gradient of every one of these elements. So we've still done k gradient calculations, but we've updated more times. And here we've done k gradient calculations and updated too. So our thought is that each epoch is going to run about the same time. Okay? Or let's not say that quite. Let's say each epoch, no matter which of these we're doing, is going to have the same number of gradient calculations. The question is bang for your buck. So if we look, for instance, at the very first epoch, we have got random parameters. So we're going to say, in the batch case, go through and for every single one of these, calculate the gradient. And then that'll tell us the direction to go. Okay. If we are way, way far off, so let's say the minimum loss is down here, and we're way, way, way up there, then clearly we want to go over in this direction. We could probably still know we wanted to go over in this direction, maybe not exactly, but we're getting closer by just looking at a subset of these. So for example, this is maybe not a great example, but let's try it. So you're on the mountain and you've got 100 campers with you, okay? So you're leading a Boy Scout or Girl Scout troop, okay? So you've got 100 campers. And you have a couple possibilities. One, you ask all 100 of them, which way do you think we should go? And then once you've asked all 100 of them, then you average their answers and go in that direction. Alternatively, you could just take a sample of 5 of them and say, which way should we go? And try and get a result. If you are way, way far off from the valley, then probably a subset of 5 is going to give a reasonably good answer, just as reasonably good answer as all 100. because everyone kind of tell, well, we need to go down there. We definitely don't want to be here. We want to go somewhere down there because this is a very bad spot, okay? Because we're way high up in the mountains. In fact, you may even just be able to ask one person and try. And the advantage then is you can update your theta. Okay. And now you're a little closer, you're a little bit down the mountain. And now you can do it again and say, like, say, ask 5 more people, right? The next 5, and say, which way do you think to go? And they'll tell you, and the next 5, and they'll tell you, and they'll tell you. So what happens is, here, after an epoch, we're not very far from the original theta. Whereas in the mini batch case, we have made k over batch size update to theta. So we have managed to make quite a change to theta. And in the SGD case, we've made a lot of changes to theta so that it can be farther along. So what size do we want to use? Well, if we look here, right, we're going to have a loop that says, let's say we're trying to pick a batch size. We'll randomize the training data set into batch size batches. And then what we're doing is we're going to do kind of for an X and Y in batch I. So, sorry, our outer loop is for num batch. So we get is for epoch equals 1 num of epochs. We randomize the training data set into batch size batches. And then for batch num equals 1 num batches, then we are going to, right, so this is all in the same code here. And then this is indented here. And then we are going to calculate the gradient of xy. And then we're going to accumulate these into an average. Once we have done this, we're going to update theta. So we're doing this within a batch number. So for every batch, we're going to update theta. And the question is, how long does this take? Okay, if you've got a batch size of 1 and a batch size of 10, does it take 10 times as long here to calculate the gradient if we have 10 gradients to calculate? And the answer is not necessarily. Let's say, for example, you have a CPU with, you have a machine with 10 CPUs. It can be that you can calculate these gradients in parallel on those CPUs. And so therefore, it's just as fast to calculate 10 gradients as it is to calculate 1 gradient because you can do it in parallel. So in that case, a batch size of 10 would be handy to have. What if you had, let's say, 1,000 processing units? Do we have machines with 1,000 processing units? Well, actually we do, right? Those are GPUs. GPUs have lots and lots and lots of processors, but they're specialized to work what's called SIMD, single instruction multiple data. That is, they can do the same thing, but operating on different data. So calculating the gradient is going to be the same calculation, but on different X and Y's. So they could do this in parallel. So depending on if you're using a GPU, that's where a lot of speed up can happen here, is that you can calculate these gradients in parallel. So how big should your batch size be? Well, in practice, what you make it is as big as you can, such that you can utilize the GPUs. Well, you're normally constrained by memory, and so increasing number of batches increases the number of XYs, and increases the space that's needed in order to calculate the gradient. And so normally, if you make the batch size too big, what will happen is you'll run out of GPU memory. So normally what you might do is, let's say, just pick a power of 2 of a batch size until you run out of GPU memory, and then back down by 1. Often you might have 256, 512. If you have large architecture or large X's and Y's, it might be 64 or 32.